Last time we talked about the observability of a linear system. Okay. So the state space presentation is what we're familiar with. Okay. So this was our system. X that equals ATX plus B of TU, and Y is CTX plus D of TU. And suppose that this is an nth order system, call it system 1. Okay. Now, what observability concerns with is that we talked about in our previous lecture. Given the information about the measurement, the output, and also the control input U, can be determined, the evolution of the state can be determined the solution X of t. Okay. And for that, eventually, we discovered that the input has nothing to do with observability, has nothing to do with that question. Therefore, without a lot of generality, the observability of this system can be studied through the observability of the simpler system, where we ignore simply the input terms. Okay. Then the question now simply is, by just looking at the output y of t, or the measurement, can be determined X of t. Okay. Now, to be able to answer that question, we introduced an object which is called unobservable subspace. So let's quickly remember what it was. Unobservable subspace for this system and for a given interval from t0 to t1 was the following subspace of Rn. Okay. So it's the set of all initial conditions that produces t0 x0 equals 0 for all times from t0 to t1. Okay. So this was the unobservable subspace for this system for the given interval t0 to t1. Okay. Now, we observed some simple but important properties of this subspace. One such property, which eventually led us to define observability, was that if this unobservable subspace is of dimension 0, in other words, if it contains only the zero vector, namely the trivial solution of this equation, then this equals y of t, okay, and a signal would have a unique solution, okay. And that produced the following, that motivated the definition of observability, which we did as follows. We said system 1 or equivalently pair CA, okay, is observable if the unobservable subspace for the given interval t0 t1 is of dimension 0 or contains only the zero vector. Okay. Now, if this is the case, then y of t equals this thing, okay, C of t, state transition matrix times x0, has a unique solution. Okay, so therefore, if the unobservable subspace is of dimension 0, by observing the output through this interval from t0 to t1, we can always figure out the initial condition x0. Okay, and if you know the initial condition of your system, clearly you can figure out the solution for all times, because you know the system parameters. Therefore, you know the state transition matrix, and state transition matrix times the initial condition produces x of t. Okay, and now we will introduce yet another tool that we will use in observability, which is called observability gradient, and it's very useful because it will help us to discover the duality between observability and controllability for LTI systems. Okay, so this is the definition of the observability gradient for a given system and for a given interval T0, T1. So given interval or end and starting point of our interval T1, T0, the observability gradient for the system, okay, here, x equals ax, y equals cx, system 1, is constructed as follows, okay? So this is notation that we use to indicate observability gradient, capital W sub O, and it's obtained through this integration from T0 to T1 phi tau T0 transpose C tau transpose C tau phi tau T0 d tau. Okay, now that the integrand is symmetric and it's something times its transpose, therefore it's also positive semi-definite, and therefore as a result the integral is also an n by n matrix, okay, because the order of the system is n, therefore the state transition matrix is an n by n matrix and it's an n by n matrix, it's symmetric and it's also positive semi-definite. Now here is a simple observation. The unobservable subspace for a given system and a given interval equals the null space of the observability gradient. Okay. Okay, it's easy to establish this. All you have to do is multiply observability gradient from left and right by x0 and x0 transpose, and then the integrand can be written as this term here, norm square, and from there everything follows. And here is an important implication of this theorem. The system is observable if and only if the null space of observability gradient is of dimension 0. So that would mean this matrix, which is n by n, is full rank. Okay, so if and only if rank of the observability gradient is n, where n is the order of our system. Okay, now we will concentrate on the LTI case. LTI case. Okay. Now consider the following pairs of systems. Okay. First, whose state we denote by x reads x that equals ax plus bu, y equals cx plus D. Okay, so we're considering the LTI case, meaning the matrices A, B, C, D are all constants. And the order of our system is N. Okay, this is our system 1. And let system 2 be denoted by the state Z. Z dot equals minus A transpose Z plus C transpose V. V is the input of the second system. And lowercase w indicates the output of the second system, where we have B transpose Z plus D transpose V. Okay. Okay, now for system 1, we can write the control Lagrangian and also the observed Lagrangian, which is just defined. So let's do that. For system 1, we have the following. Controllability Lagrangian reads WC T0, T1. Suppose that this interval from T0 to T1 is given. So that can be written as T0 to T1 e to the A T0 minus tau B transpose e to the A transpose T0 minus tau d tau. Okay, so that comes from the definition of controllability Lagrangian for the first system. Likewise, the observability Lagrangian, which we just defined, T0, T1, remembering that the state transition matrix phi T0 is simply e to the A T minus T0 for the LTI case. We can easily write the observability Lagrangian for our first system, system 1. Okay, which is e to the A transpose tau minus T0 C transpose C e to the A tau minus T0 d tau. Okay, so nothing out of ordinary. And what we're going to do is we're going to do the same thing this time for system 2. Note that system 2 has parameters that are related to the parameter of system 1 in a peculiar way. The A matrix of system 2 is minus A transpose. Okay, since A is n by n, minus A transpose is also n by n. Therefore, the second system is also an nth order system. The B matrix of second system is the output matrix transpose. Okay, output matrix of the first system transpose. And likewise, the C matrix of the second system is the input matrix of the first system transposed, and similarly for D. Okay, so you take everything, you transpose it, and for the A matrix, you put a minus sign in front. Okay, now let's go ahead and do the same thing, that is write down the Lagrangians for the second system. And then once we did that, we're gonna notice something that will be very, very useful for our later analysis. Okay, now for the second system, we have the controllable Lagrangian W of C to differentiate between the Lagrangians of the first system and the Lagrangians of the second system. Let's put a bar on the Lagrangians for the second system. So the controllable Lagrangian of the second system for the same interval is T0 to T1 e to the A transpose tau minus T0 C transpose C e to the A tau minus T0 d tau. Okay, and then we do the same thing for the observable Lagrangian. T0, T1, okay, the integral e to the a T0 minus tau b transpose to the a transpose T0 minus tau d tau. Okay, and immediately we recognize that the observable Lagrangian of the first system equals the controllable Lagrangian of the second system, and the controllable Lagrangian of the first system is the observable Lagrangian of the second system. So therefore these two systems are related in a peculiar way through their gradients. Okay, so let's put that observation down, which will be very helpful very soon. Note that. And the controllable Lagrangian of the first system. Okay. Now, what can we make out of this peculiar observation? We can make a lot of things, so let's see how. Okay. Now, we can proceed as follows. Okay. So system 1 is controllable if and only if the controllable Lagrangian is full rank. Okay, so that's one of the first results that we obtained about controllability in our previous lectures. Rank omega c equals n. Now, rank omega c equals n is same thing as rank, not omega c but wc, rank w bar o is n, because this Lagrangian, observable Lagrangian of the second system, is same as the controllable Lagrangian of the first system. Okay, therefore this is just rewriting what we have here. And then the rank of the observability Lagrangian of some system being full means that that system is observable. Okay, system 2 is observable. Okay, now get rid of the middle steps, the Lagrangians, and what we have obtained is quite remarkable. This is what we've obtained. The system 1, okay, is controllable if and only if system 2 is observable. Okay, so controllability of one system implies the observability of the other system. Now this is perhaps easy from the mathematical point of view, but from the actual thing, from the psychological point of view, that's quite hard to grasp, okay? Because controllability and observability are quite different things. And in fact, such equivalence doesn't exist, as far as I know, for the general nonlinear systems. Okay, so what we have obtained is the following. If the pair is controllable, then the pair CA, by CA I mean C of the second system and A of the second system, and C of the second system was B transpose and A of the second system was minus A transpose. So this pair is controllable if and only if the pair B transpose minus A transpose is observable. Okay, so let's give this important discovery a number. Okay, that's our relation 3. Now let's get rid of this minus sign. How we can do it is by eigenvector test. Then AB controllable, okay, if and only if minus AB controllable. Okay, now why is this true? Remember the eigenvector test for controllability. A pair AB is controllable if and only if no eigenvector of A transpose belongs to the null space of B transpose. Now, since the eigenvector of A and eigenvectors of minus A, they're identical, they're the same. Okay, therefore, if the system is controllable, then by eigenvector test, okay, if the system is controllable, then and only then the system minus AB or the pair minus AB is controllable. And then if pair minus AB is controllable by what we have just obtained, the pair B transpose minus A transpose is observable. Okay, so that's how we can get rid of the minus. BAT is observable. Okay, so let's write down what we have established. Okay, hence we established the following very important fact. We established that AB, a pair AB, is controllable if and only if pair B transpose A transpose is observable. Okay. Or equivalently, pair CA is observable, okay, if and only if pair A transpose C transpose is controllable. Okay, because of this relation between the observability and controllability of transposed systems, these two concepts, observability and controllability, are said to be dual concepts for LTI systems. Okay, so as far as I know, that duality doesn't have a natural extension to the nonlinear domain. Okay, due to this peculiar relation, controllability and observability are said to be dual concepts for LTI systems. For linear time invariant systems. Okay. And there is also an important implication of this duality from the analysis point of view. Note that we have established many important results on the controllability of LTI systems, and now using those results and this duality, we can obtain the duals of those controllability results for the observability of an LTI system, and we will start doing this very soon. Okay, now let's therefore start making use of this very important property, namely duality between observability and controllability. Okay. Thanks to which we will have many theorems without really needing to prove. Now, given the pair CA, let's define the dual of controllability matrix. Okay, we're going to call it the observability matrix. Define the observability matrix as follows. The observability matrix is the following matrix with n columns, okay, and n times n rows, where n is the size of the output vector. So the first n rows come from the output matrix C. The second set of n rows come from this product, output matrix multiplying A, and you keep doing that until you reach the n minus first power of A. Okay, if you have a scalar output, if the output is scalar, then this matrix, the observability matrix, becomes a square matrix n by n, where n is the order of our system. Now, here is a theorem that relates this observability matrix to the observability of the system. Okay, remember that. Remember the dual result. If a system, a pair AB is controllable if the controllability matrix is of rank n. Okay, if it's full rank. Likewise, the pair CA is observable if and only if, okay, where A is an n by n matrix, if and only if rank of observability matrix is n. Okay, is n. Okay, so A is an n by n matrix. Okay, here is one line proof thanks to duality. Now, the pair CA observable is equivalent to the pair A transpose C transpose is controllable. Okay, so that means the corresponding controllability matrix is of rank n. Okay, so the rank of the controllability matrix. Okay, what's the controllability matrix? It's B, A, B, A square B, and so on. But now, instead of A, we have A transpose. Okay, instead of B, we have C transpose. Therefore, the controllability matrix is C transpose, A transpose, C transpose, and A n minus 1 transpose times C transpose. Okay, so this has to have rank n if this pair is controllable. And clearly, if the rank of this matrix is n, the rank of its transpose is also n, and if you transpose this matrix, you obtain the observability matrix, okay, from which we obtain rank of observability matrix equals n. Therefore, the observability of a system can be checked through its observability matrix. Just construct the observability matrix and make sure that it has n linearly independent columns, or equivalently, if the rank that it has rank equals n being the order of the system. Okay, now here is a less obvious result about observability. The unobservable subspace for a given interval t0, t1, we're talking about an LTI system, turns out to equal the null space of the observability matrix. Okay, now let's prove this important equality. Now, the null space of the observability matrix, now the observability matrix is here, by using one of the fundamental theorems in linear algebra, can be written as, and we use this relation many times before, range space of observed matrix cis transpose cis orthogonal complement. Okay. So null space of this matrix, or any matrix, is the orthogonal complement of the range space of its transpose. Okay. And then let's write this as range space of, okay, so what's the transpose of observable matrix? This is our observable matrix and its transpose is here. So let's write that down. C transpose, A transpose, C transpose, and A transpose n minus 1 times C transpose, and then whatever that subspace, we take its orthogonal complement. Okay. And then this clearly equals range space of C transpose, and then instead of A transpose we write minus A transpose C transpose, and so on, minus A transpose and minus 1 C transpose orthogonal complement. The reason is that here we have some columns, okay, and range space of that matrix is the subspace spanned by the columns of this matrix. Now clearly if you put some of those columns, if you multiply some of those columns with minus 1, what they span will not change. It should be the same subspace. Therefore, range space of this matrix and range space of this matrix, where instead of A transpose we have minus A transpose, must be the same. And as a consequence, their orthogonal complements must be the same. Now, the reason that we replace A transpose with minus A transpose is because we want to use the Gramian, okay, or the duality between the Gramians. So that's the range space of the controllability Gramian of the second system. And then we take the orthogonal complement. Okay, remember, WC bar was the controllability Gramian for the pair minus A transpose C transpose. Okay, so this was the A matrix of our second system, and C transpose was the B matrix of our second system. Okay, now range space of the controllability right. So this is the controllability matrix of the second system, and therefore, since the range space of the controllability matrix same as the range space of the controllability Gramian, that from an earlier result we moved on the next line. Okay, and then this, we use this fundamental theorem once again. This can be written as the null space of something, and that's null space of this matrix is transpose. Okay, the controllability Gramian of the second system transpose. And then this equals the null space of the same matrix, because Gramians, both observability and controllability Gramians, they are symmetric matrices. Therefore, we can get rid of the transposition. And we noticed just recently that this Gramian is same as the observability Gramian of the first system. Okay. WO, where WO is the observability Gramian for the pair CA. Okay, and then we know that that's related to the unobservable subspace. In fact, it's no other than the unobservable subspace. Unobservable subspace from T0 to T1. Okay. So that's the proof of our theorem, where we used very nicely the equality between the controllability and observability Gramians of the dual systems. Okay. Now here the left hand side is null space of a matrix, and that matrix is time invariant because it's constructed using constant matrices CNA. And on the right hand side we have a subspace that seems to be depending on some interval T0 and T1. Since we have established this equality, unobservable subspace therefore is independent of the interval for an LTI system. Okay, no matter what T0, T1 you choose, T1, as long as T1 is larger than T0, you always have the same subspace, and that subspace is the null space of the observability matrix. Okay, now let's obtain some more results using duality. Okay, it's a very quick, cheap way of writing down theorems because we don't really have to prove them. Okay, now let's dualize the eigenvector test of controllability to an eigenvector test for observability. Okay. Here is our eigenvector test for observability. The pair CA is observable if and only if, okay, no eigenvector of A belongs to the null space of the output matrix. Okay, null C. And here is the one-line proof, which will directly follow from the eigenvector test for controllability plus the duality between observability and controllability for LTI systems. Okay, so the pair CA is observable by duality if and only if the pair A transpose C transpose is controllable. And now here we have the controllability of a statement regarding the controllability of a pair, and in that case we can use the eigenvector test. So this pair is controllable if and only if, okay, no eigenvector of, okay, so call this A tilde and this is B tilde. The eigenvector test for controllability was the pair A tilde B tilde is controllable if and only if no eigenvector of A tilde transpose belongs to the null space of B tilde transpose. Okay, therefore let's rewrite that statement here. No eigenvector of A tilde transpose, which is A transpose transpose, belongs to the null space of B tilde transpose, which is C transpose transpose. Okay, put another parenthesis here. Now, since A transpose transpose is A itself and C transpose transpose is C itself, we have this eigenvector test for observability. And similarly, or just another way of writing this eigenvector test is called PBH test. Okay. So we have now the PBH test for observability. The pair CA, or the system x equals AX and y equals CX, is observable. Okay, if and only if we have this rank condition satisfied. A minus lambda I C equals N for all scalars, okay, on the complex plane. Okay, Now, what else we can say about observability? To answer that question, we have to remember what other theorems we had for controllability. We have the Lyapunov test for controllability, which is valid for exponentially stable systems. So let's dualize that nice theorem to observability. This is the Lyapunov test. Okay, for observability. Suppose that the system x that equals ax is exponentially stable. Okay, that is, a has eigenvalues only with strictly negative real parts. Then the pair CA is observable if and only if there is a unique solution which is symmetric positive definite, okay, matrix to the Lyapunov equation. To the Lyapunov equation. Okay, which reads ATP plus PA equals minus C transpose C. And here is the other version of Lyapunov test theorem. This is the Lyapunov test backwards, okay. Lyapunov test backwards, by which we mean, now here the statement is valid under the condition that the system is exponentially stable. And then what we do in the backward theorem is we will start with the assumption that the pair CA is observable. And then if that's the case, we can claim that this equation, the Lyapunov equation, has a solution if and only if the system is exponentially stable. Okay. Now suppose the pair CA is observable. Okay. Then the system x that equals AX is exponentially stable if and only if we can find a P a symmetric positive definite matrix which solves, and turns out that it solves it uniquely. It's a unique solution. Okay, the Lyapunov equation satisfying ATP plus PA equals minus C transpose C. Okay. Now, to get an idea on why that result should hold, well, first of all, we don't have to prove it because we already proven their controllability versions. Okay, and then since observability and controllability, they are dual concepts for LTI systems. All we have to do is just apply proper transposition to A matrices and replacement of B and C matrices, and immediately we obtain these theorems. Okay, but still, to get some idea, let's prove part of the second theorem statement. Okay. Consider the following example. Let the pair CA be observable. And there exists a symmetric positive definite matrix P that solves the Lyapunov equation. ATP plus PA equals minus C transpose C. Prove that, okay, which is what's being stated in the theorem. Prove that x dot equals AX is exponentially stable. Okay, so what we do is, here is a solution. What we do is we just pick an eigenvector of A and then multiply both sides with its transpose and the vector itself, and from there, plus the eigenvector test of observability, we will reach easily to exponential stability. Okay, so here is a very nice solution. Let V, an n-dimensional vector, be an eigenvector of A with eigenvalue lambda. Okay, lambda in C. In other words, we have AV equals lambda V, and V is a non-zero vector because it's an eigenvector. Okay, then we can write the following: V conjugate transpose times. So what we do is we take this minus C transpose C to the other side, and what we have is ATP plus PA plus C transpose C equals the zero matrix. Okay. ATP plus PA plus C transpose C equals 0. It's just another way of writing the Lyapunov equation. And then, since this thing is 0, multiplying from left and right by V and V conjugate transpose and V will not make anything different. And now we still have this 0 here. Well, previously it was a matrix 0, now we have scalar 0. Okay, now let's play with the terms. Here we have V conjugate transpose times A transpose. Since A is a real matrix, that can be written as AV conjugate transpose times P. And then V, another V is coming from the other side, and we have V here. Okay, plus V conjugate transpose PA V. Okay, and we have V. Okay, we have V conjugate transpose times C transpose times CV. Again, C is a real matrix, therefore we can write this as CV conjugate transpose times CV. Okay, now AV is lambda V, so let's rewrite that. We can have, so this equals lambda times V, and then we're taking its conjugate transpose. That produces lambda conjugate times V conjugate transpose PV plus. Here we have AV, which is lambda V. Lambda is a scalar. We can take it to the left and write lambda times V conjugate transpose PV. Okay. And finally, this is a vector conjugate transpose times itself, therefore it's the Euclidean norm square of that vector. Okay, so we have CV norm square. And while we're doing that, we have 0 on the left-hand side. Now, here we have V conjugate transpose PV, and here we have the same thing. One is multiplied by lambda star and the other is by lambda. Therefore, we can write this as lambda star plus lambda times V conjugate transpose times PV. Now, lambda star plus lambda is, now since star means conjugation, it equals 2 times the real part of lambda. So this we can write as 2 times the real part of lambda times V conjugate transpose PV, okay, plus CV norm square. Okay, so let's see what we know. V conjugate transpose PV is strictly positive. Why? Because V is a non-zero vector, because it's an eigenvector, plus P is a symmetric positive definite matrix. Therefore, by definition, this will produce a positive scalar. So this is positive. What else? This thing is also positive, okay? Why? Because of the eigenvector test. Since the pair CA is observable, no eigenvector of A can belong to can belong to the null space of C. Therefore, C times V cannot be 0. If CV is a non-zero vector, therefore its norm is positive. As a result, its square of the norm is also positive. Okay, so what we have therefore is, here we have 0 and here we have this time this plus a positive number that gives us 0. Therefore, this thing here, the whole thing, must be negative. Since this is positive, it's only possible if the real part of lambda is negative. Okay, so that implies that the real part of lambda should be strictly negative. And that means, since lambda was an arbitrary eigenvalue, it means all the eigenvalues of our matrix A is with strictly negative real parts. As a result, the system is exponentially stable. Okay, so that's a nice application of the eigenvector test, or a combination of eigenvector test and the Lyapunov test.